What is a PLC? Beginner's Guide to Industrial Automation. For the Control Brainiac. Have you ever stopped to think about how massive factories operate with such precision? Machines assembling thousands of products a day, conveyor belts moving in perfect timing, robotic arms placing components with unbelievable accuracy. No human operator pushing buttons non-stop. No chaos. Just pure coordination. From packaging your favorite snacks to assembling vehicles on high-speed production lines, even controlling elevators in massive skyscrapers. There's one powerful little device working behind the scenes, quietly making all of this possible. The PLC, or Programmable Logic Controller. In this beginner-friendly guide, we're breaking down everything you need to know about PLCs, what they are, how they work, and why they are absolutely vital in the world of modern automation. Whether you're a student, a technician, or just curious about how machines work, this is the perfect place to start. Let's dive in. What is a PLC? So, what exactly is a PLC? A programmable logic controller is a type of industrial computer that's designed to control machines and automated processes. Think of it like the brain of an automation system. It's always paying attention, watching sensors, checking signals, making split-second decisions, and then triggering the correct response. But unlike your desktop computer or smartphone, PLCs are built for much tougher environments. We are talking about places with extreme temperatures, hot, cold, and everything in between. Dusty or humid air, often with oil mist or water vapor. Strong electrical noise from nearby motors and welders. Constant vibration from heavy machinery. PLCs are made rugged because they need to operate reliably in these demanding conditions, 24 hours a day, 7 days a week. At its core, a PLC does three essential things in a continuous loop. Reads inputs like sensors, buttons, or switches. These tell the PLC what's happening in the system. Processes logic based on a control program you write. That all changed when an engineer named Dick Morley introduced the very first PLC, built for General Motors. The goal was simple. Replace those bulky, inflexible relay panels with something programmable, a controller that could be updated with software, not screwdrivers. It was a game changer. Since then, PLCs have evolved dramatically. Today's PLCs are smaller and more powerful, able to communicate over Ethernet and wireless networks, capable of advanced functions like real-time monitoring, data logging, and even connecting to the cloud. Modern PLCs are helping drive the Industry 4.0 revolution, enabling smart factories, predictive maintenance, and remote diagnostics. Main components of a PLC. Let's open the hood and look at the key parts of a PLC system. There are four main components you'll find in just about every setup. 1. CPU, Central Processing Unit. This is the brain of the PLC. It's where the logic lives. The CPU is constantly scanning inputs, running your program, and updating outputs, all in fractions of a second. It also manages communication with other devices and performs diagnostics. 2. Input-output modules, I/O modules. These modules are the PLC's sensors and muscles. Input modules take in signals, like a sensor detecting an object or a button being pressed. Output modules send out signals, like turning on a motor, opening a valve, or triggering an alarm. 3. Power supply. Every PLC needs power to run. The power supply takes standard AC voltage and converts it into the low-voltage DC power needed by the CPU and other modules. 4. Programming device. Usually a laptop or PC with specialized software. This is where engineers and technicians create the logic that tells the PLC what to do. Once the program is ready, it's downloaded to the CPU and the system is live. How PLCs work, the scan cycle. Now let's talk about how a PLC actually works in real time. PLCs operate in a continuous loop called the scan cycle, and it happens over and over again, incredibly fast. Here's how the cycle works. Input scanned, the PLC reads the current state of all input devices. Program execution, it runs the control logic using those input values. Output update, it updates the status of all output devices. Diagnostics and communication, the PLC checks for faults and communicates with other systems. Let's look at a real-world example. Imagine a packaging line with a conveyor belt. A box arrives at a sensor. The sensor sends a signal to the PLC. The PLC processes the logic and turns on a motor to move the belt. Another sensor detects the box reaching the next station and the PLC stops the motor. A robotic arm might then pick up the box for sealing or labeling. All of this, from detection to decision to action, happens in just milliseconds. That's the power of the PLC scan cycle. Programming a PLC. So how do you tell a PLC what to do? You program it using special languages defined by the IEC 61131-3 standard. The most common one is ladder logic, a graphical programming language that looks like electrical circuits. It's easy to read, especially for electricians and technicians. Each rung of the ladder represents a condition and a result. For example, if start button is ON and stop button is OFF, then turn ON the motor. Other programming options include function block diagram, FBD, great for process control and visualizing logic as blocks. Structured text, ST, a text-based language, similar to Pascal or Python, ideal for math and loops. Sequential function charts, SFC, perfect for step-by-step operations like mixing or batch filling. Modern programming platforms like Siemens TIA Portal, Allen Bradley Studio 5000, or Mitsubishi GXWorks provide drag-and-drop tools, simulators, and online monitoring. These features make PLC programming easier than ever, even for beginners. Real-world applications. So where do we find PLCs in action? Honestly, just about everywhere there's automation. Here are a few real-world examples. Manufacturing plants running robotic arms, conveyor belts, and quality inspection systems. Water treatment facilities monitoring pump levels, adjusting chemical dosing, opening and closing valves. Elevators and escalators managing floor selection, door operation, and safety features. Traffic light controlled adjusting signals based on sensor data and real-time traffic conditions. Theme parks coordinating ride timing, safety interlocks, and special effects. Whether it's food, cars, energy, or entertainment, if machines are running automatically, chances are a PLC is making it happen. Why PLCs matter plus outro. In today's world, automation is everywhere. And PLCs are the invisible heroes behind that automation. They are fast. They are reliable. And they are engineered to last, often running 24/7 for years without failing. If you're exploring a career in industrial automation, robotics, mechatronics, or electrical engineering, then understanding PLCs is one of the best foundations you can build. We hope this video helped you get a solid start in the world of PLCs. If you found this helpful, don't forget to like the video, subscribe to the Control Brainiac, and tap that notification bell so you never miss a new tech breakdown. Thanks so much for watching, and we'll see you in the next one.